Okay, today we're starting the complex numbers unit of specialist mathematics for the QCAA curriculum. But let's be honest, you need to learn complex numbers. So the way we're going to start to build the complex numbers. This is the first lesson. The first thing, I squared equals -1. That is the number one thing. Highlight it, bold it, circle it, do whatever you want. You need to know that. Minimum. That is where I comes from. I equals -1. That is why complex numbers and imaginary numbers exist. Now, the reason we have complex numbers is when you learn quadratics, you know, negative b plus or minus, all that garbage, right? When the discriminant is less than 0, there are no solutions. Well, that's what you learn. However, what if I told you there were no real solutions? Real. However, there are complex solutions. See, this is -2. Just becomes 2i. Just an I. Now all of a sudden it has solutions. Look at that. That's one of the many reasons, but that is a major reason we have these things. So complex numbers are a set of numbers. So in complex numbers, there is the real and imaginary part. And we can plot this on an Argand diagram. Argand diagram we can learn later. But the main thing you need to know is we deal with the real parts and the imaginary parts separately. They go together. And so, for example, this example, 4 minus 3i equals 2a plus bi. 2a equals 4. You see the two real portions of the actual equation go together to form a equals 2. Then -3i equals to bi, and b equals -3. So we pair each version. And so we pair the complex part and the real part of the equation to form and solve these equations. This is pretty simple. Now, according to up here, the form that we need to start building these complex numbers in is a plus bi, where a is the real part and b is the imaginary part, where bi is the imaginary part. However, a and b have to be an element of real. That's a b. Special r. That looks like a b, but it doesn't matter. It's the weird bubbly r that you've learned. I know you have. And so a and b must be real. Otherwise this whole thing falls apart. And now, here's another example. To find the real values of a and b such that 2a plus 3b plus a minus 2bi is equal to -1 plus 3i. And now we can just do simple. Man, why am I so... Man. We literally learned this in matrices. We learned how to do this in matrices. You get the two equations, simultaneous equations. Man, El Bozo gene today here. So you get the two simultaneous equations. You match. This is the real part, and this is the real part of what's on the other side. So you match those two up, and you match the imaginary part with the imaginary part. You following? Hey, this is important. Listen to this. You multiply 2 by 2. Whoa, what does that mean? 2a minus 4b equals to 6. That is our third equation. When you subtract 3 from 1, you get 7b equals to negative 7. Therefore, b equals negative 1 and a equals 1. Now, this is all a bit much for you, probably. But we can organize these with z. So z1 equals to that, and z2 equals to that. And so to find z1 plus z2, it equals to that, and then we take the two real parts and put them together, and we take the two imaginary parts and we put them together. And in the end, we're left with negative 2 plus 2i. Now, in multiplication by a real constant, it's literally exactly the same as every other algebra. You don't need to learn that. You already know. You're taking specialist mathematics and you're taking hard mathematics. I don't have to teach you that. Now, powers of I. This is important. Listen up. These work in sort of a, I like to think of it as like a circle, a unit circle, if you will. Now, it's not really a unit circle, but if we think of it, if we're going round and round the circle, right? And so here we have 1, we have I, negative 1, and negative I. And that's how we go. Now, if we go I to the power of 0 equals to that. And I equals to I to the 1, because that's just I. This is important. You remember this from the top of the page? I squared equals negative 1. This is what this whole thing is based off. And I cubed equals to negative I. And so, if you notice, you're kind of just like orbiting the circle. So, you see here, 0 plus 4 equals to 1. So I to the 0 and I to the 4 both equal 1. I to the first power and I to the fifth power both equal I. I to the power of 1, the power, if you add 4 to the power, you're back with the same answer. You end up with the same answer. And so this is where you get these 4 laws. This is where you get these 4. 4 times n. N is just any number. Well, any integer, I must add. 4n is just equal to 1. 4n plus 1 is equal to I. And like I said here, you're just going around the circle. So that's pretty easy. How about we get on to some questions, eh? Let's start. State the values of the real and imaginary of z for each of the following. Let's do all of them, shall we? Now for A, Re of z equals to 2. Im, imaginary of z, equals to 3. You see that? Real equals 2, I equals 3. The component equals 3. And for B, we do the same thing. Real of z is 4. And the imaginary component of z is 5. We keep going. The real component of z for question C is a half. The imaginary component of z is negative 3 over 2. You see that? I can match them up. You see this? You just end up matching up the I, the imaginary component, and the real component. This is how we find these values. Moving on. Question 2. Find the real values of a and b in each of the following. Now, if we just see 2a plus bi is equal to 10. Now, if you'll notice, there's no imaginary component. Therefore, bi is equal to 0. Therefore, b is 0. Simple enough. And now if we do the real component, 2a is equal to 10, a is equal to 5. Because we matched up, we'll use this color, we matched up the real component with the real component, and we matched up the imaginary component with the imaginary component. In this case, it's actually imaginary, because it's 0, because there is none. But it's pretty simple. Moving on. Now if we do question D, we can match up the two real components. 3a equals 2. Therefore a equals 2/3. I don't think I have to explain that to you. And therefore, if we match up the imaginary component, a minus b is equal to 1. And if we can just sub in 2/3 minus b is equal to 1. And then we can just go 1 minus 2/3 is equal to negative b. And so 1/3 is equal to negative b. Therefore, negative 1/3 is equal to b. Simple enough? Okay. Moving on. We do 3g. Now, because, as you can see here, there are imaginary components and real components inside each of the brackets, we're going to need to expand the brackets first. And so, if we just expand the brackets, 8 minus 12i minus 2 minus 8i. Now we can match up the two real components. 8 minus 2. 8 minus 2 is equal to 6. And negative 12 minus 8 equals negative 20. Therefore, is equal to 6 minus 20i. I think we'll need to add more space here, but we can work with this for now. If we do h, we have the same problem, real and imaginary components. So we're going to need to expand the brackets again. Negative 5 plus 4i plus 1 plus 2i. Negative 5 plus 1 is equal to negative 4. And 4 plus 2 is equal to 6. Therefore, is equal to negative 4 plus 6i. I think you get the point, right? You know what? For the heck of it, I'll do some more. Where is it? Let's insert some space here. Let's insert some space. Let's get some more space in here. Well, I guess H is still up there. H is down here. I and J. Now, they're being a bit tricky here. They've put the real component in the second half. Oh, man, what's going on? They've put the I okay. Regardless, you can see they've put the imaginary component first, whereas in all of the ones above, real component, real component, real component, real component, real component, real component, they're second. They've tried to be sneaky here, So 5i plus 20, we once again expand the brackets, plus 6i minus 21. Now if we do 5 plus 6 equals 11, and 20 minus 21 is equal to negative 1. And now, for my sanity's sake, let's put the real component first, eh? Negative 1 plus 11i. And now for j, they haven't tried that on us, so we're good. We now expand the brackets as 2 minus 3 over 2i minus 3 over 2 times 2. Man, what is this specialness? Negative 3 over 2 times 2 over 1. You can just cancel them. Equals 3. Minus 3. I over... No. What? What's going on? Yeah, 3i over 2. It take me so long, man. 3i over 2. Wow, would you look at that? So 2 minus 3 is equal to negative 1. That's the real component. You know what? Let's do that. I think that's actually how it's supposed to go. And then we can say the imaginary component of z is equal to negative 3i on 2 minus 3i on 2. And now it stands to reason that we can say 6i on negative 6i on 2 and we can just do this again, 3i, negative 3i, because we can just cancel this, 3 and 1, therefore equals to negative 1 minus 3i. Simple enough? We move on. This is the fun stuff. We're getting to the fun stuff now. Now, this is where all of those powers of I come into play. What did we remember I to the third power was? Negative I. I don't know if you got that right. I'm hoping you did. You're a smart kid if you did. So negative 2i times negative I. Seems simple enough, hey? Have I just had a mind blank? Have I just like forgotten? Oh no, we're good. Equals to negative 2i squared. But if you remember I squared is equal to negative 1. Therefore, negative 2 multiplied by negative 1 equals 2. That's what we got. Now h, 4 times I to the power of 4 times 3 I to the power of 2. What do you remember about I to the 4? It's 4 plus I to the 0, and I to the 0 is 1. You should all know that. 4 times 1 times 3 times, we just did it over here, negative 1. Therefore, 4 times negative 3 equals negative 12. The fabled surd. Now, 8 I to the 5. What's I to the 5 minus 4? Because that'll get us somewhere in it within our circle. 2. Am I right? No. No, I'm an idiot. Okay. Oh, okay. Yeah, that'll just get us I, because 5 minus 4 equals 1. And I to the 1 is just I. So this equals to 8i times, and we need to what's wrong with this? We learned last year, probably for you, that you can't have a negative 7, correct? Well, yes you can. You just have to put an I on the end. Therefore, root 2i equals 8 root 2i. Wow. Wow. Okay, we move on to 5c. Root 2i times I is equal to root 2i squared. And then root 2i times negative root 2 is equal to, what happens when you times two roots that are the same together? Bingo! You're left with negative 2. I. Wow. And then this is just negative. Yes. This is just negative root 2. Therefore, it equals to negative root 2 minus 2i. We move on. Negative root 3 times root 3i. It's the same situation, exactly the same situation as we had over here. We're equal to negative 3i. And then negative root 3 times root 2. Say it with me now. Root. Who am I kidding? You know how to multiply roots. Negative root 6. Negative root 6. No, you can't simplify root 6. Can you? No, I don't think you can. Minus 3i. And that, my friends, is the end of our time together. I shall spend more time with you now. Who cares, man? Go away, bro. Stop doing maths, you. Stop being... No, that's alright. It gets harder from here.